He went on to get his PhD from the College Park math department. And his mentors are Michael Fu and Bill Massey, whose work I'm familiar with. So it was kind of exciting to see that connection here. And he is, I think, it seems to me that is an abstract that I understood a little bit. He's going to talk about queuing theory. And the talk, he's currently working for Noblis in Fairfax. And the title of the talk is Performance Analysis of a Multi-Class Preemptive Priority Call Center with Time-Varying Arrivals. Ahmad.
Okay. Oh, I'm sorry. Yes. Of course. Full screen. There you go. All right. Good afternoon or morning. My name is Dr. Ahmad Ridley. I am M1. I'm going to talk a little bit today about performance analysis of a multi-class preemptive priority call center with time-varying arrivals. This is work that I did for my dissertation with my co-advisors, Dr. Michael Fu at University of Maryland College Park, and Dr. William Massey, who's at Princeton University. So I'm just going to give you a little introduction of call centers. Some of you may be familiar with call centers. If you don't know the definition of them, I'm sure you've interacted with them, and I'll go over that a little bit. Just state the problem that we were working on, some research contributions. In other words, where my research fit into the overall landscape of the work that's been done on this problem. Talked a little bit about the fluid approximations model that we developed and compare it to a simulation model. And after that, I'll show some computational experimental results and summarize those results and talk a little bit about future research in the area. Okay, so call centers are basically groups of trained or experienced agents that provide some kind of resource to customers who call in. It could be customer sales or any other kind of support service. Incoming calls are handled promptly and connected to available agents. Hopefully, that's the case. Customer calls are hopefully satisfied with the least amount of resources possible. And when we say resources here, we're primarily talking about the people, the agents who answer calls. So how many of you, from just that little bit of a definition, think you know what a call center is? Well, okay, very good. For those of you who may not understand, anytime you call your bank, your credit card company, phone company, complaining about your bill, or any other kind of customer service, maybe the Motor Vehicle Administration, and you have to hold for a person to talk to, you're interacting or you're interfacing with a call center. In the late 1990s, call centers evolved to more than just phone calls over the regular phone network. Nowadays, you can send emails, you can even do a web chat with some call centers. You can still do faxes if you choose, and of course, you can always pick up the phone and make a call. There's been greater emphasis on using computer applications to actually provide customer information to the agents before they actually talk to a person. From your interactions with call centers, I'm sure you called up and gotten the automated system, which is called the Interactive Voice Response Unit, and they've asked you either to enter a phone number, an account number, or some other kind of identifying information. With CTI, that information pops up on the screen of the call agent so that when you are connected to them, they'll already have your name, address, recent calls that you've made, recent inquiries that you've made prior to that phone call, so that they're more able to assist you, and hopefully at a faster pace. CTI makes this possible. Unfortunately, at least I've noticed that when I do give that information and the person picks up my call, they asked me for the information again. So it was kind of, what was the point of me typing in that information if you're just going to ask it again? In those cases, that information may not be pushed to the agent. And also CTM, this whole customer relationship management, is this whole process of managing your interaction with the call center. They want to make it as easy as possible and as friendly as possible for you to access them, because you represent a business to them. So they don't want to drive you away because that represents a potential loss of revenue. So for basic call center operations, there are a couple of components. One of the ones I've already mentioned is interactive voice response unit. It handles customer transactions automatically. A lot of the times, if you just need to find directions to a location or the hours that a business is open, you won't need to talk to a person. You can just get that information from the interactive voice response unit. If you need to check an account balance, or when your bill is due, or when your last payment was received, a lot of that information is done you can access automatically, and that frees up the people to answer other calls that may require more work to solve. And agents answer incoming calls based on call attributes, and which leads into a little bit of research that we're doing. Not all calls are the same. Some calls have higher priority than others. You may have a customer, if you're a bank person with a lot of money stored, saved at your location, they will receive higher priority than someone who doesn't have as much. So there are different standards, and when those people call, they expect or they receive a slightly different level of service. They may pay for that, but they receive that. So the problem that we were solving is finding the optimal number of agents necessary to meet service level requirements. And to do that, we compare performance measure estimates using this fluid approximation model and a simulation model. And the performance measures that we looked at were mean number in system and mean virtual waiting time. The reason that finding a number of optimal agents is important or worthy of research is that about 70 to 80% of the cost of running a call center from a business perspective, from a manager's perspective, is spent on the labor, the salaries and training of the agents who actually answer the calls. This is one of the reasons why you have a lot of call centers outside of the U.S., places like Ireland, Tunisia, South Africa, the Philippines, and of course India. This type of process, it's a discrete state stochastic process, and we use queuing theory to model it. And I say discrete states because we're tracking the number of calls that enter the system. So those are integer values called discrete state space. And typically they're modeled, this process is modeled as a queuing theory problem. And the notation MT/M/N represents the arrival process is modeled as an exponential process. And the number of arrivals that enter the system is modeled as a Poisson process. And the T on that first letter there represents that the arrivals vary by time. So typically for a call center, you have maybe it's a bimodal distribution where maybe in the late morning you have a spike, and in the early afternoon you have a spike in calls. In the very early morning or the very, very early evening, the amount of calls level out. So that could represent right before lunch, people may make a lot of phone calls, or right after lunch, they may make a lot of phone calls into these different call center environments. So we model the arrivals, the arrival times as exponential, as having an exponential distribution, the number of arrivals as a Poisson process, and the service times, the rate at which agents answer calls, we're modeling as an exponential distribution, and the N represents the number of agents that are in the system. And for my research, we divided the types of calls into two, voice calls and emails. So I mentioned this multimedia call center. And nowadays, people can not only reach agents over the phone, but they can also reach them over emails. I've had a couple of experiences where I'm actually on the phone waiting, and the message while I wait states that you can also check out this information online if you need to. So they're driving you towards their website, and on their website, they'll have a link for you to contact the call center through email. Some may not even list a phone number. So they want you to move towards this type of interaction to kind of lessen the volume of voice calls. So in this model, we have voice and emails. Voice is considered high priority because that's the people who are talking or interacting with a call center over the phone. We want to make sure they have the least amount of delay as possible. We don't want them to wait any longer than they have to because they could abandon the call, just hang up. Emails are less volatile to a delay. Usually when someone sends an email to a call center, they don't expect a response in a minute or so. Maybe the next day or two, if they get a response, they're satisfied with that. So we classify that type of traffic or type of interactions as low priority. However, one of the different contributions to this research is that emails have dynamic priority. So an email may enter the system as a low priority, but after a day or two, if the email has not been responded to, we can change the priority level to high priority to make sure that the emails are receiving some level of customer service. You can imagine if there's a spike in calls, in voice calls, the voice traffic would dominate the email traffic. And so the agents will spend almost all of their time answering voice calls and may never get to emails. But we want to provide the emails a certain level of performance. And so we classify this dynamic priority, or changing from a low priority to a high priority, as the low priority calls abandoning their original location or queue and moving into a high priority queue. And for the fluid model, we modeled the abandonment time, or this process of switching priority, as exponentially distributed with rate 1 over the service level. Typically for emails or low priority traffic, in this case, service level is about 24 hours. Nowadays, I think a lot of call centers are guaranteeing at least 24-hour return if you send a response, if you send a question or comment through email. And with the simulation, we use a constant value of 1 over the service level, S. And we modeled the agents as having the skill level to answer voice and emails. A lot of times, you may have two separate pools of agents, some who just answer voice calls, which is the predominant type of traffic or interaction with a call center, and then a separate group who answers emails. Well, here we're pooling them together into one resource and assuming they can answer both types of calls. And for the arrival process, I mentioned before, it's a non-stationary Poisson arrival process, and the service times are exponentially distributed. Non-stationary meaning that the time in which calls arrive, the rate at which calls arrive can vary over the course of time, particularly over the course of a day. And this is just a kind of a picture of the model that we're working on. So you see there where you have Q1 of T and Q2 of T, those represents the two Qs. Q1 for the high priority calls and Q2 for the low priority calls. And as calls come in, they first interact with the IVR, the Interactive Voice Response Unit. That's the automated system that you first meet when you call a call center or 1-800 number of some sort. And the calls are split virtually into two different queues, two different waiting lines. And based on the number of calls that are in the system, to our right, where we have this rectangle with numbers 1 through N, those represents the agents, the N agents that answer the calls as they come in. And based on your call type, the service rate or departure rate is defined as U1 times Q1 with that notation to the N. That notation, that caret there, represents the minimum of N, the number of agents, and Q1, the number of high priority calls in the system. And we have a similar type rate for the low priority calls. So this just models the flow of calls through the call center. So the research contributions in this area are an application of a fluid approximations preemptive priority two-class multimedia call center. Under this type of dynamic where we have two types of calls and where we allow low priority calls to switch priority, the application of fluid approximations is fairly new. My advisor, Dr. William Massey, worked on this problem with fluid approximations, but it was under a different type. The traffic was all one type of traffic, no high or low priority, and the rate at which calls leave the queue and enter service was a first come, first served basis. That's kind of a standard service model. But here we have a preemptive priority. And I guess I should define, I'm sorry, preemptive priority. Preemptive priority means that if an email is being serviced by an agent and there's a voice call that comes in to the system before the agent has finished responding to the email, the agent will abandon or leave the email and answer the phone call. And then once the phone call is finished, they'll go back and answer the email. So in that sense, the emails are being preemptive by the voice calls. So with these fluid approximations, this is the first time we kind of applied this model to this, this technique to this type of model. And actually, fluid approximations are actually they model continuous phenomenon. You can think of fluids as water or gas. And what we're talking about here is a discrete state process where we're counting the number of calls that come into the system. And so the application of these types of calls to queuing theory is somewhat new. So I mentioned the preemptive priority service with abandonment to generate dynamic priorities. That was another contribution, how to handle low priority calls being switched to high priority calls. And the development of this low priority waiting time algorithm. Basically, how does that process work? And this is just a flow chart of when do you allow the low priority calls, these emails, to switch priority to a high priority level. You have, if these calls are in queue, they have an abandonment time, the amount of time they're willing to wait before they switch, and service time. So we monitor the minimum of these times as the process goes on to determine when that happens. So just some notation on the fluid approximations model, Q raised to the 0 is the fluid approximation performance measure for the number in the system, and the corresponding model for W is the waiting time of a virtual customer arriving at time tau. And we rely on some strong law of large number results to show that as n goes to infinity, as the scale factor goes to infinity, these results will approximate our queuing model results. And the reason that this happens is from a result derived by Drs. Halfin and Dr. Witt called the Halfin-Witt regime, where they scale up the number of arrivals and the number of servers. Again, I mentioned that fluid approximations are for continuous processes. We're dealing with kind of a discrete state process. And the way that these work together, the reason that this approximation works in our example is that once we scale it up, our discrete state problem models a continuous problem. And these are differential equations here that model the change in the number of high and low priority customers in the system using that diagram that I talked about before. You have arrivals and departures into the system. Typically, for a real-world problem of this complexity, folks will develop a simulation model. So for my research, I developed a C program to model the queuing theory process. And when all else fails, you can write a simulation to model the system. But what we were looking at is comparing these fluid approximation results to the simulation model. Simulation model works well, but it takes a long time to run. The results that I get from the simulation model on the order of hours, where with the fluid approximation results, you have somewhat analytical results that you can write down, and it takes minutes to run the model. Again, an important result about scaling the fluid results in order to get a good comparison to the simulation model is stated here. And we looked at the different arrival rate functions for both models. Arrival rates where the system was underloaded, meaning the offered load was less than the number of agents, and overloaded situations where there were more calls in the system than the agents can handle, which case the calls would have to wait for service. And these are some of the results, computational results, variables that are defined here. And we define values we use for the service rate, the scale factor. Once we scaled the arrival rates and number of servers up to about 35, we were able to get good results. The time interval, we modeled this over the course of a 12-hour day for a call center. And the target mean waiting time for the high priority calls, it's about 30 seconds or half a minute. Usually for call centers, they try to answer about 85% of the calls within 30 seconds. That's a typical performance measure, standard. And for the low priority calls, we use 90 minutes here. So here are the results. Unscaled, we compared the number in the system performance for these fluid and simulation models. And you see that the graphs are not close. The fluid approximation result on top is in blue, and the simulation result is in green. The simulation result we know is a good way to model the system. We're trying to show that the fluid approximations model also is a good model of the system. And so these graphs should overlap. And then this is also for the waiting time. You see the graphs do not overlap. But once we scale up the arrival rates and number of servers, we see that our fluid approximations model does in fact match the simulation model, which is a good result. And this is for the, so this is for the number in the system, and this is for the waiting time. Once we were able to get the performance measures to reach our target, we looked at how many servers would be required in order to meet that service level. Remember, that was the problem that I stated before, finding the optimal number of optimal number of agents to guarantee a certain performance measure for certain service level. And these numbers, the 700 represents the scaled up number for the servers. But you see, as we increase the number of servers, we're able to reach performance for the delay, the percent of high priority delays and low priority delays above 90%. And for in the simulation result, so I should go back. For the fluid approximations model, we see the number of servers was 730. In the simulation result, it was slightly more for at 745.
I think you have 30 seconds to wrap up.
Okay, sure, thank you very much. So in summary, we showed that using the scaling approach that Dr. Halfin and Witt developed, we can get good estimates from our fluid approximations model to our simulation model. The fluid approximations is more scalable than the simulation. We're only solving two differential equations to get our performance measures, whereas with the simulation, we have to do a lot more work to model the system for the number of servers. Okay. And one last statement. I mentioned here that our agents were assumed to be able to answer both types of calls. In future research, you can divide up the skill level of different agents and route calls based on skill. So I'll stop there.
We ran over a little bit, so we will eliminate the question and answer session. Oh, you have a question? No. Oh, you get it. All right. Honestly, is the overall.
Okay.
Any quick question for him? Yes.
I have a question. So
yes.
What you were modeling there was pretty much a two-priority system with the abandonment. Have you guys thought about looking at how to use this same model for a much more complex system? Like how would you add factors where you need to maybe like at certain times you have to switch for certain things. Maybe this task says we need it for this amount of time, but we can wait later and stuff like that.
Right. So part of the future research is to, I don't know if I mentioned it there, was to add in more types of calls and different types of behavior, such as abandonment, the voice calls. Some people can just abandon the system if they're waiting too long. Different types of calls like interactions like web chat, faxes, where the flow of the calls are different than what we modeled here. We've actually done some research on that and modeled that. You can expand this instead of just a 2-class case to N classes of cases. So, good question. Okay, thank you.